The first law states that a body at rest will stay at rest, and that a body in motion will stay in motion. Without a force, all objects will continue moving in the same direction with the same speed forever. Objects here on Earth slow down only because of the force from friction and air resistance. The second law states that objects change their motion when a force is applied. An object's change in motion is the strength of the force divided by the mass of the object. This means that it is harder to change the motion of objects with more mass. When all forces are removed, the object's speed will stay constant. If we watch the previous scene again, we will see that the moment Victoria exerts a force against the train instantly also exerts a force on her. This is what causes Victoria to move backwards. The two forces are exactly equal in strength, and they are in exactly opposite directions. The third law states that for every action, there is an equal and opposite reaction. When Victoria's feet move against the earth, she is creating the force pushing her forward. Victoria's feet moving against the earth also creates an equal and opposite force pushing the entire earth in the opposite direction. But because the mass of the earth is so large, the impact of this force on the earth's motion is extremely small. For larger forces, the impact on the Earth's motion is no longer negligible. According to the first law of motion, the Earth will want to continue moving in a straight line. According to the second law of motion, the gravitational force from the Sun will want to cause the Earth to fall directly into the center of the Sun. Note, in Einstein's theory of relativity, gravity is not a force but a curvature in space-time. This will be discussed later in this video. According to the third law of motion, the Earth will exert an equal and opposite gravitational force on the Sun. Since the Sun's mass is much bigger than the Earth's mass, the impact on the Sun's motion will be negligible, but the impact on the Earth's motion will be significant. The first law of motion wants the Earth to continue moving in a straight line. The second law of motion wants the Earth to fall directly into the Sun. The result is that the Earth follows a path in between these two options. This is what causes the Earth to orbit the Sun. Just as the Earth's forward motion prevents it from falling directly into the Sun, this is also what allows a roller coaster to travel upside down. The ball's forward motion allows it to continue traveling upward against the force of gravity. If the ball's forward motion is fast enough, the ball will continue moving along the track, and gravity will not have enough time to cause the ball to fall off. Suppose we apply a force to a rotating object. Each point on the object will want to continue moving in the same direction as before. These 2 points will cause the object to move like this. And these 2 other points will cause the object to move like this. The events shown here all happen at the same time, and this is the result. This means that when we apply a force to a rotating object, its rotation is changed to look like this. This creates the illusion that the force was really applied 90 degrees ahead in the rotation. This has profound implications for our everyday lives. Let us consider the rotating wheel of a bicycle. When Victoria leans in one direction, this creates a force on the wheel. However, because the wheel is rotating, the result is that it will appear as if the force is applied 90 degrees ahead in the rotation. This will cause the entire bicycle to rotate like this. This is why leaning causes a bicycle to change direction. It's also why objects that normally fall over almost instantly are easy to balance when they are spinning. This happens because the gravitational force always appears to be applied 90 degrees in advance of the direction in which the object is about to fall. But this will not work if the object stops spinning. This is the reason why it is easy to balance a bicycle when the wheels are spinning rapidly, but nearly impossible to balance when the bicycle is standing still. The purple sphere at the North Pole is standing still. If we apply a force and ignore friction and air resistance, the purple sphere will follow this path. Since the Earth is rotating relative to this path, the sphere's path will look like this to people on the ground. The spheres at the equator are moving faster than all the other spheres. If we apply a force away from the equator, the first law of motion will want the sphere to keep moving around the Earth faster than the other spheres. From the perspective of someone on the ground, the sphere will appear to veer towards the east. Therefore, objects moving from the equator to the North Pole will veer in the opposite direction as objects moving from the North Pole to the equator. Suppose we have a low-pressure area, and the air molecules around this area experience a force towards the center. The air molecules experiencing a northern force will veer in the opposite direction of the air molecules experiencing a southern force, causing a rotation. This is the reason why hurricanes rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. All the laws of motion are always riding with us, including the third law.